So in this video, what I want to do is to give you practice in writing down partial fraction decompositions. And these are very often needed in integration, but I don't want you to actually calculate these integrals. I don't even want you to calculate the values of the coefficients. What I want you to do is to look at each of these three integrals in turn and say, how would you rewrite the integrand in terms of arbitrary unknown coefficients, and just write those down. That's the starting point. So how would you write this down? How would you write this down? And how would you write this down? Think about it, write down what you believe it to be in terms of unknown coefficients, and then come back and we can discuss the answers. So see you in a few minutes. Okay, let's look at the first one on the next slide. So let's look at the integrand in this example. And what we see is that we have a proper rational function. The highest power of x in the numerator is x to the 1. If we were to expand this out, the highest power of x would be x cubed. There would be an x squared from here times x. So this is higher than the highest power here. And we see that we have got two factors. There's a linear factor here and another linear factor which is repeated. So this is repeated, and it is repeated twice. So what this tells us is that this is going to be of the form a over x minus 1 squared, plus there could be a subleading term, b over x minus 1. And if you'd chosen to write these first two terms the other way around, say as a over x minus 1 plus b over x minus 1 squared, that's obviously perfectly fine, and it just means that you're redefining what's a and what's b. But at the end, you're going to calculate a and b in an application. Okay, and then the other term is going to be plus c over x plus 3, because that's a linear factor. And then what you would do is you would put these onto a common denominator. This would be the common denominator, and you would find three equations for three unknowns. You would solve them and find out what a, b, and c are. I'm not going to do it in this video. Let's look at the next example. So in this example, we have got a proper rational function. The highest power of x here is x to the 4th. If we multiply this out, we have 2, 3, 4, because this is squared, 5 powers of x. So it's x to the 4th over x to the 5th. This is a proper rational function. And this factor here is squared, so it's repeated twice. This is not an irreducible quadratic. It vanishes when x is 0. And this term here is also repeated twice. This is not repeated. So this is going to be of the form a over x squared plus b over x plus c over x plus 2 squared plus d over x plus 2 plus e over x plus 1. So in other words, what we do is we say, well, this has to be at least x squared here. So a is not going to be 0 to give us this term. But there could be a term like that hidden inside this structure. We have to assume it's possible. Then here, there must be a term, c can't be 0, of the form x plus 2 squared in the denominator, but there could be a subleading term as well. And then there must be a term involving 1 over x plus 1. So that is our answer for this. And again, if you put this on a common denominator, which must be this denominator here, you would end up getting 5 equations for 5 unknowns, and one could solve them. I'm not going to bother doing it in this video. Let's look at the third example. So in our third example, we have a linear term repeated twice. We have an irreducible quadratic. This term here can never be 0. The smallest it can be is 1, because it's 1 plus something squared. So the smallest it can be is 1 when x is 0. So this is never going to vanish, and it's also repeated. So for the x squared, what we must get is something like a over x squared plus perhaps a subleading term, b over x, plus cx plus d over x squared plus 1 squared, and at least one of these two coefficients cannot be 0 because we need to get this in the denominator, in the same way that a cannot be 0 to give us this in the denominator. And then there can be subleading terms here again, ex plus f over x squared plus 1, no longer squared. So subleading in powers of x squared plus 1. So that is the general structure that you can have here. But over here we've got a very simple numerator, and we actually notice something rather beautiful. So I want to write this down. By symmetry, the left-hand side, so this side of the equation, is unchanged under x goes to minus x. So if I replace x by minus x here, I'd get minus x squared, which is x squared, and minus x squared, which is x squared here. It would not change. So that symmetry must be preserved over here. Now here it's preserved, here it isn't. So therefore b will be 0. Here it's preserved, and the d, of course, is not changed. It's a constant if x goes to minus x, but here it changes. That tells us c must be 0. In the same way, e must be 0 and f doesn't have to be. So we see, therefore, that 1 over x squared times x squared plus 1 all squared has a partial fraction decomposition of a over x squared plus d over x squared plus 1 all squared plus f over x squared plus 1. So there are actually only 3 unknown constants for us to calculate. And in principle, f could be 0, but it might not. I haven't actually taken the trouble of working out what it is. But by symmetry, we can say that the other terms must vanish. Now, often you don't have symmetry. If we'd had, say, 1 plus x here, then this would have changed under x goes to minus x, and these arguments would not apply. But if you have symmetry, use it. It makes life much, much easier. And with that, I'll stop this video.